I'll illustrate some of the concepts with a graph problem. So this is a graph. These are the nodes. They represent areas of a university, and these are the edges. Now, a sequence of edges where the second element of the first edge matches the first element of the second edge, the second element of the second edge matches the first element of the third edge, and so on, is called a path. It's an x1 to xk path if the first element of the first edge is x1 and the second element of the last edge is xk. So, for example, here is a path from main quad to Gregorian. Another path goes this way. Now, a cycle is a collection of edges that form a path starting and ending at the same place. So here the dark edges form a cycle. A set of edges in a graph is spanning if for every edge of the graph there's a path in the set of edges connecting the two endpoints of the edge. For example, let S be the set of dark edges in this diagram. This is a spanning set. For example, consider the edge between biomed and athletic. Its endpoints are connected by a path using edges of the set. The edge from main to kini, its endpoints are connected by a couple of paths among the edges in the set. So this is a spanning set. Now, later on we'll understand the connection between this use of spanning and the use in connection with vectors. A set of edges in a graph is a forest if the set includes no cycles. So, for example, the set of dark edges illustrated here is not a forest because there's a cycle here. If we remove one of those edges, the resulting set of dark edges is a forest. The minimum spanning forest problem is a fundamental problem in graph algorithms. The input is a graph and an assignment of weights to edges. And the output is a set of edges that is spanning and a forest, and subject to those requirements has minimum weight. So this might come up, for example, in an application in which you must select some of these edges to form a network that can deliver hot water between different areas of a campus. The network must achieve the same connectivity as the input graph, and the edge weights represent the cost of installing pipes between the endpoints of the edges. And the goal is to find a set of edges that's spanning and is of minimum cost. It'll turn out, because the edges all have positive weight, that the solution will be a forest. Let's consider algorithms for this fundamental problem. There are two natural approaches you might take to coming up with a solution. One is called the GROW algorithm. Given a graph, start by initializing the set S to be the empty set, and consider the edges of this graph in increasing order of weight. For each edge in turn, consider whether its endpoints are already connected by a path using edges in the set S of edges selected so far. If not, add that edge to the set S. If so, move on to the next edge in increasing order of weight. Let's try this out. The first edge is the weight 2 edge. Now, so far, we've selected no edges. So certainly, these endpoints are not connected using the edges selected so far. So we'll add this to our set of selected edges. Next edge is 3. All right, the endpoints are not yet connected, So we'll add this edge. Next is 4. Its endpoints are not connected, so we add that edge. 5. Oh, now the endpoints of the edge with weight 5 are already connected using edges we've selected. So we skip 5. Moving on to 6. Its endpoints are not connected, so we add that edge in. 7. Its endpoints are not yet connected, so we add that edge. 8. Oh, its endpoints are already connected using a path of edges already selected, so we skip 8. And 9. Its endpoints are also already connected. We've run out of edges, so that's our solution. Is it indeed a minimum spanning forest? Here's another natural algorithm for solving the minimum spanning forest problem. I call it the shrink algorithm. You start by initializing S to the set of all edges. And now you consider the edges in decreasing order of weight. For each edge in turn, if removing that edge still leaves a path among the selected edges between the endpoints of the edge, then go ahead and remove that edge. Let's try it out. We start with the heaviest edge, the one of weight 9. Now, removing this edge will leave its endpoints connected using the edges we haven't yet removed. So we can cross that out. Now we go to 8. Removing the edge with weight 8 is safe. We go to 7. Removing the edge with weight 7 would leave the endpoints of that edge without a path between them among the edges we've kept. So we don't remove 7. 6. If we remove the edge with weight 6, there won't be a path between its endpoints among the edges we haven't yet eliminated. So we leave that in. 5, well, we can remove this edge because its endpoints are connected using edges we have. 4, if we remove this edge, there won't be a path, so we leave that in. 3, the same, we leave that in. And 2, we better leave that in. So this is the set of edges selected by the shrink algorithm. Is this truly a minimum spanning forest? You might have noticed that the GROW algorithm for minimum spanning forest closely resembles the GROW algorithm for building up a set of generators. And the shrink algorithm for minimum spanning forest closely resembles the shrink algorithm for finding a possibly smallest set of generators. It's not a coincidence. We can formulate minimum spanning forest as a problem in linear algebra. So here we start with a graph. We'll let D, the domain of our vectors, be the set of nodes. Now we can represent a subset of D by a vector over GF2. We just put a 1 in every position represented in the set. So the set Pembroke, Main, and Gregorian is represented by this vector, which has 1s precisely in the positions Pembroke, Main, and Gregorian. So here's the representation of all the edges in this graph. For example, the edge between Pembroke and Athletic is represented by this vector that has a 1 in Pembroke and a 1 in Athletic, and the rest are zeros. Now, the vector representing the subset Keeney-Gregorian, this vector, is the sum of the vectors representing the set Keeney-Main, Main-Riston, and Riston-Gregorian. So let's see that. Here's the vector for Keeney-Main. Here's the vector for Main-Riston. And here's the vector for Riston-Gregorian. If we add up these vectors, the ones in this column sum to 0, the ones in this column sum to 0, and we're just left with 1s in the positions Keeney and Gregorian. Now, a vector with 1s in entries x and y is the sum of vectors corresponding to edges that trace out an x to y path in the graph. In this case, the path from Keeney to Gregorian through Main and Riston. So here's another example. Each of these sets represents one of the edges, shown in dark here. The span of the corresponding vectors contains, for example, the vector Main-Keeney, because there's a path from Main to Keeney using those dark edges. It contains the vector Keeney-Gregorian, because there's a path from Keeney to Gregorian using those edges. But it doesn't include, for example, the pair Athletic and Biomed, because there's no path using dark edges between those two nodes. Similarly, it doesn't represent the pair Athletic and Main, or Biomed and Main, because there's no path of dark edges connecting those two nodes. Here's the GROW algorithm for minimum spanning forest, and here's the GROW algorithm for vectors. Considering the edges of the graph corresponds to considering vectors in the vector space. Testing whether an edge's endpoints are connected using edges we've already added to S corresponds to testing if a vector lies in the span of the vectors we've already selected. So the GROW algorithm for minimum spanning forest is a specialization of the GROW algorithm for vectors. We can force this to make choices that exactly mimic the execution of this algorithm.